Hi there. In this video, we're going to be taking a look at the electromagnetic spectrum and how we can use a couple of equations to allow us to convert between different measurements of the waves within that spectrum. And those measurements help us to define characteristics about that wave. It helps tell us about the wavelength, the frequency of that wave, and the energy that's produced by that wave of light. And so, as you can see from this figure here, the electromagnetic spectrum as a whole is quite large. It extends over many orders of magnitude in terms of wavelength. So that you see that at the kind of the longer end of the spectrum at radio waves have the longest wavelengths, and they're in the tens or hundreds of meters. And if we go all the way to the other end of that electromagnetic spectrum, we're into the 10 to the minus 13 meters, or hundreds of femtometers. Okay, so all the way from 10 to the second to 10 to the minus 13th. So a huge range for those wavelengths. And you can see that these wavelengths or that these types of radiation are arranged from long wavelength to short wavelength, so radio waves being the longest, gamma rays being the shortest. And that order also corresponds to the frequency and the energy of those waves. So the shorter a wavelength is, the higher its frequency is, right? As we go from radio waves on one end to gamma rays on the other end, those wavelengths are getting shorter and shorter and shorter and shorter. And so the number of those wavelengths that could pass by any given point in the same amount of time gets higher and higher and higher. So as you squish the wave together more and more and more and more, you can get more of those waves to pass you by in the same amount of time. So as wavelength gets shorter, frequency gets higher and higher and higher. Okay? And so frequency is also related to the energy of that wave. And so what we see is that frequency is directly proportional to energy. So as frequency goes up, so too does energy. So the waves that are shown in this particular figure go all the way from low energy down at radio waves up to high energy at gamma rays. Okay? And we see that visible light there, kind of in the middle of that scale, is this small, tiny little sliver in between infrared and ultraviolet light. So that little tiny sliver of the electromagnetic spectrum is the only part that our eyes are sensitive to. Okay, and that's, we define much of our world through what we can see, through this tiny narrow band of that electromagnetic spectrum. Okay, and so again, the energy of that visible light, okay, is defined by its frequency and then in turn by its wavelength. Okay, and so we see where visible light is on the scale, just higher in energy, so just higher in frequency, so shorter in wavelength, is ultraviolet light, and that's where that term ultraviolet comes from, right? We see visible light, our sort of familiar Roy G. Biv spectrum. Okay, so red, orange, yellow, green, blue, and violet. And so violet is the highest energy of visible light. Okay, it has the shortest wavelength, you see around 400 nanometers. And so the shortest wavelength means the highest frequency. Highest frequency means highest energy. Okay, so violet light is the most energetic of visible light. Even more energetic than violet is ultraviolet. Okay, and so you see red in the visible spectrum has the longest wavelength at around 700 nanometers. 700 nanometers, that longer wavelength, corresponds to a lower frequency. That lower frequency corresponds to lower energy. Okay, and so red light is the least energetic of visible light, and just less energetic than red light is infrared light, or inferior to red light. All right, so let's take a look at some of those equations that we can use to define those characteristics of wavelength, frequency, and energy. So what we see in these equations here, we see the first one is that C is equal to lambda times nu. Okay, so the Greek lowercase lambda, all right, is our symbol for wavelength, and the Greek lowercase symbol nu is our symbol for frequency. Right? And so these two quantities, wavelength and frequency, as we said before, are inversely proportional to each other. So as one goes down, the other must go up. Okay? As wavelength gets shorter, frequency goes up. Right? So these two are inversely proportional to each other. And so we can set the product of those two equal to some constant. And the constant that we are able to use is the speed of light. So wavelength being in a length unit, okay, and frequency being in a time unit, okay, so in fact it's seconds to the -1 or 1 over seconds, okay. So length times frequency, that product that we would get, the units would be length over time. Okay? And so length over time is a way to describe velocity. And so the velocity that we'll use here is the speed of light. So the equation that we see here, c equals lambda nu. C is that speed of light in a vacuum, okay, which is equal to 3 times 10 to the 8th meters per second, or 300 million meters per second. So that c is equal to lambda times nu. Okay? So because those two are multiplied together, as one goes up, the other has to go down, or vice versa. Right? And so if we know the frequency of light, we can use this equation to calculate wavelength. If we know the wavelength of light, we can use that same equation to help us calculate the frequency. Right? The thing we have to keep in mind here is that speed of light is in the units of meters per second. Okay? And so because of that, we need to make sure that our wavelength is in the units of meters and that our frequency is in the units of per seconds, or hertz. Okay? The other equation that we'll use is a way to calculate the energy of that light. And what we see here, this equation is E equals H times nu. So energy in joules is equal to a constant times frequency. So what this equation says is that frequency and energy are directly proportional to each other. As one goes up, the other must go up. Okay? So as frequency gets higher, energy gets higher. Right? And so that constant, that H, is called Planck's constant, and it has this value here, 6.63 times 10 to the minus 34 joule seconds. Right? And so what that means is that the energy that we'll get is going to have the units of joules, okay, because our Planck's constant is in joule seconds. Right? And so that means that our frequency value has to be in hertz, or per seconds. Right? So we always want to use these equations, we always want wavelength to be in the units of meters, and we want frequency to be in the units of hertz, okay, or per seconds. Right? So let's see if we can try using these equations to help us to calculate either the frequency or the wavelength of light. All right, so the question that we have here is, what is the frequency of 450 nanometer light? Okay, so what's the frequency of this length unit of light? Well, that's 450 nanometers must be our wavelength. Okay, and so what we're being asked is that if we know the wavelength of light, can we calculate the frequency? Right? And so what are the steps that we need to follow to make this conversion, or to do this calculation? Our first step is that we have to use our equation here, this C equals lambda nu. We need to solve that equation for frequency, right? Frequency is what we're trying to solve for, so we want to solve for that unit of, or that variable nu, okay? And so we can say that C is equal to lambda times nu. And so how do I solve for nu? Well, I would divide both sides of this equation by lambda. Okay? And now on this side of the equation, lambda in the numerator and the denominator are going to cancel. And so what I'm going to be left with is that C over lambda is equal to nu. Right? And so if I know the speed of light, which of course I do, it's constant, and I know wavelength, I can calculate frequency. right? So I know my equation, and so now I just need to plug those values in. But of course, before I do that, I need to remember that the units for wavelength that I want to use in this equation is going to be meters, because speed of light is in meters per second. All right, so the next step here is that I need to make sure that lambda is in the right units, and that units that I'm looking for is meters. So what we're told in the problem is that the wavelength of light we have, lambda, is going to be equal to 450 nanometers. Okay, so the trick is, how do I convert that into meters? Well, a couple ways we can do that. One, we can just think about how do we slide the decimal in order to get this from nanometers to meters. And so if we read our table here, what we see is that if we're sliding from nanometers, okay, if we're going to slide from nanometers up to the base unit of meters, then we would want to slide the decimal 9 places to the left. Okay, and so we can do that. We can slide the decimal 9 places to the left, and what we would get is that lambda is equal to 0.00000450. Okay, and that would be in meters. Okay, and if I wanted to, I could take that unit, or I could take this measurement and put it into scientific notation. And so if I do that, lambda is going to be equal to, let's see, I'm going to move the decimal place 1, 2, 3, 4, 5, 6, 7. I'm going to move it 7 places, and I'm going to be sliding the decimal to the right here. Okay, and so that exponent is going to be negative. So we're going to have 4.50 times 10 to the minus 7 meters. Right? So that's our wavelength in meters. And so we can slide the decimal, turn that number into scientific notation. Well, another way that we can do this, and okay, it's not technically quite correct scientific notation, but it's a little bit of a shortcut way to get this number 450 nanometers directly into scientific notation. And so if we go back and consult the table, one of the things that we see, right, is if we look here, we see that nano is 10 to the minus 9 as we compare it to meters. And so what this column says is that there are 10 to the minus 9 meters in a nanometer. Okay, there are 10 to the minus 9 meters in a nanometer, right? And so some dimensional analysis that we could do there is to say, okay, how many meters are equal to 450 nanometers? Well, I know that there's 10 to the minus 9 meters in every 1 nanometer, right? So nanometer is going to cancel on the top and bottom. There's just now a 1 left in the denominator, and so what I've got is 450 times 10 to the minus 9 meters, right? And so if I can remember that there are 10 to the minus 9 meters in a nanometer, then I can really quickly put 450 nanometers in kind of quasi-scientific notation, right? So 450 nanometers is equal to 450 times 10 to the minus 9 meters. Okay, and if I wanted to convert that to, technically correct scientific notation, right, then I would take this implicit decimal here and slide it 2 places to the left, okay, which would, sliding the decimal 2 places to the left would make my exponent more positive, and so this would become 4.50 times 10 to the minus 7 meters, right? Point being, if you can remember that kind of relationship between meters and nanometers, that there are 10 to the minus 9 meters in a nanometer, then you can really quickly put things into quasi-correct scientific notation. So we're going to remember that our wavelength is equal to 450 times 10 to the minus 9 meters. Okay, all right. All right, well, now that I know that my wavelength is 450 times 10 to the minus 9 meters, I've got everything that I need to solve this problem, right? Before, we figured out that frequency was going to be equal to c over lambda. And of course, I know that c is equal to 3 times 10 to the 8th meters per second. And now I know that wavelength is equal to 450 times 10 to the minus 9 meters, okay? And so when I do this division, right, what's going to happen to the units? Well, meters are going to cancel, and I'm going to be left with the units of per second. So I'm going to be left with the units of hertz, and that's the kind of frequency unit that we're used to, okay? So let's do this math together. Let me So let's start with 3 times 10 to the 8th divided by 450 times 10 to the minus 9. Okay? And so when we do that division, we get 6.67 times 10 to the 14th hertz or per seconds, right? So that's converting from wavelength to frequency, right? And so we can do lots of practice problems in which we're kind of going back and forth between frequency and wavelength, and that equation or that process is always going to be the same. We're always going to be solving for either frequency or wavelength. And of course, I could rearrange this equation and say that wavelength is equal to the speed of light over frequency. Okay, so it's always whichever one we're looking for, we're taking the speed of light and dividing it by the one that we have. Okay, so it's always speed of light on top and the thing that we're looking for, or the other kind of measurement that we have on the bottom. Right? Okay. All right, so let's try another one. So in this one, we've got what is the wavelength of an AM radio station at 1280 kilohertz? Okay, so if you didn't know that, FM radio stations are measured in megahertz and AM radio stations are measured in kilohertz. Okay, so those measurements are the frequency of those radio stations. It's the frequency of the waves that are being emitted by that radio tower. And so if I know the frequency, I can calculate the wavelength because those waves are moving out from that radio tower at the speed of light. Okay? And so if I know the speed of light and I know the frequency, I can calculate wavelength. And so our first step is to solve our equation C equals lambda nu for lambda, for wavelength. And of course, we've done that before, right? So we know that C is equal to lambda nu. If we want to isolate lambda, then we can divide both sides of the equation by nu. Nu cancels on the top and bottom over here. And so lambda is equal to the speed of light divided by frequency, right? And so step 2 now in this equation is, can I convert frequency, which is currently in kilohertz, can I convert it to hertz, right? Okay, and now that we've got our table back up, we can take a look and, all right, so how do we convert 1280 kilohertz into hertz? Well, if we look at our table here, one of the things that we can see is that for kilo, what we see is that there are 10 to the third of the base unit in 1 kilo of the base unit. Okay, so there are 10 to the third hertz in 1 kilohertz. So if I want to convert from kilohertz into hertz, I can do the same thing as before, right? Remember before I used the 10 to the minus 9th. Now I'm going to use the 10 to the third. So 1280 times 10 to the third is that frequency in kind of our quasi-scientific notation, right? Because we could do the dimensional analysis and say how many hertz are equal to 1280 kilohertz. And what we would say is that in every 1 kilohertz, there are 10 to the third hertz, okay? So kilohertz cancels on the top and bottom, and I'm left with 1280 times 10 to the third, right? So we've got our frequency in hertz, okay? 1280 times 10 to the third. All right, and so now we're ready to solve this equation, okay? And so we know that we know that lambda is equal to C over nu. We know that C is equal to 3 times 10 to the 8th meters per second. And we know that our frequency is 1280 times 10 to the third, 1 over seconds or per seconds or hertz. Okay, all of those things are the same thing. So 3 times 10 to the 8th divided by 1280 times 10 to the third. Let's put that in our calculator and see what we get. So we've got 3 times 10 to the 8th divided by 1280 times 10 to the third. And what we get is 234, and I'm just going to round it to there, 234 meters. Okay, So remember, our visible light was around 400 times 10 to the minus 9 meters. Okay, and now we've got our radio wave at 234 meters. So radio waves are a billion times longer than visible light waves. All right? Okay, let's try another one now, but with our other equation of converting between energy and frequency. Okay, so in this first question here, we're being asked to calculate the energy of light at a given frequency. Okay, and so we have this equation here that E is equal to h nu. Energy in joules is equal to Planck's constant, which is this 6.63 times 10 to the minus 34, times frequency in hertz. Okay, and so, well, this is just kind of a plug and chug kind of a situation here, right? Because we're looking for E, and we know that E is equal to h times nu. We've got nu in hertz. We know what h is, and so we just need to multiply them together. So E in energy is going to be equal to 6.63 times 10 to the minus 34, okay, times our frequency, which is 4.45 times 10 to the 14th. Okay, and I'm sorry, I didn't write units there. So joule seconds times per seconds, okay? That means that seconds is going to cancel, and we're just going to be left with joules, right? So let's do that math in our calculator. So we've got 6.63 times 10 to the minus 34, and we're multiplying that by 4.45 times 10 to the 14th. And what we get is 2.95 times 10 to the minus 19 joules, okay? So energy is equal to 2.95 times 10 to the minus 19 joules. Okay? And so for visible light, so the frequency of visible light tends to be in the 10 to the 14th hertz range, and energy of visible light is in this kind of 10 to the minus 19 range.